Welcome. Thank you for your time for another technical talk today. The topic today is safety and security with contract-based design. Many of you might have, especially the ones who work in automotive, have heard safety multiple times in the past, according to these standards which are derived from the ISO 15118. No, 61508. Sorry, this I was at charging. So derived from the 61508, which is on functional safety. But this is not all the story. So this is these standards are very well process oriented, but having a safe and secure system is always also connected to your real technical implementation, which of course has to be supported by processes. And today we will learn about architectural patterns and backgrounds to make a system more secure and safe. And this is due to the support on an architectural level to ensure integrity of your system and to ensure that you do the technical checks. So it's a more technical oriented solution, which is usually more appealing for engineers, but it's really, really helpful because it gives you a powerful instrument at an early conceptual stage during development, and thus really ensuring a higher level of safety and security within your system if you apply consequently and if you, for example, use the right tools for this. And I'm very grateful and happy that Thomas Schütz will lead us through this technical talk today again, and will share some of his deep knowledge which he acquired working on different systems in telecommunication, automotive, and medical, which are all domains which have a great focus on both safety and security. So you will learn from the expert. Thank you very much, Thomas, for joining today and giving us the opportunity to show our highly experienced network and to share some very valuable, deep technical know-how. And I will go out now more or less from the meeting, and I hope you really enjoy it. I'm always happy to listen to Thomas and to learn more. Thank you.
Yeah, thank you, Annette, for the introduction, and I'm glad to be here. So today I'm going to talk about safety and security with contract-based design. So why we need safety and security? I guess if you're here, you might have an idea what it's about. So safety, it's about saving lives or preparing people of becoming injured, something like that. Security is information security, access security, and so on. And both are closely related in many systems. So if you hack a system, you can somehow, so it's a security problem, but you could somehow break the system in order to cause a safety problem in a car or in a medical application or something like that. So they are cause-effect related. And but there are also similar technical issues you need to address that are similar in safety and security systems. So you want neither system to break. So, and the usual approach is to design a system, make an architecture, implement it with certain rules, and then test it in order to find problems with safety and security. Today, I'm going to show you a very different approach. So how can we construct a system to be basically unbreakable? There is no 100%, of course, also not with contracts. But how can we construct a system in a way that it's inherently much more robust, and this helps with safety and security. So now let's get started with the meat. So what's the problem? The problem is, imagine you have a traffic light, a pedestrian crossing, for example, or a crossing in a street. So if both directions of the traffic lights show green, this might cause some trouble. This might cause accidents, loss of life, and so on. So that's something we want to avoid. So how can we avoid this erroneous behavior in a complex software and system? So that's the main question here. How can we? The first problem is, how can we describe what we want? Usually it's a textual requirement, so the two traffic lights must not be green at the same time. Okay, that's the requirement. The next step is, how can we prove that in a very complex software system, or in general in a very complex system, we hold this requirement? Yeah, we do unit tests, we do integration tests, we do acceptance tests, hill, mill, pill, sill, whatever it is, testing. The problem is the test cases themselves are, again, very complex software, especially not in a unit test maybe, but in a unit test, you do not prove the system, that the system is working. You only prove small components and small integrations. So how do we prove that the system itself works correctly? Usually, to do that, in order to do that, we need complex test environments and complex tests. So, and am I really complete there? That's the big question. So the testing helps, but usually most bugs are found very late in the process. And if they're found very late in the process, the costs for fixing them, for retesting them, and so on, they grow exponentially. That's another aspect. It's not only loss of life, but it's also a cost aspect. So even for non-safety and security relevant systems, you still have the cost problem if you detect an error very late in the process. Not just one more aspect here. So now imagine you have a specification and you have source code, structure models, behavior models, whatever it is. And imagine you can formulate a contract that describes exactly what you want in a more formal way than just a textual notation, and some magical mechanism that verifies your application, whether it holds the contract, whether it implements the contract correctly. This would be a very nice thing to have. So not a text and a test case that tries to match the text to the code or whatever it is, but really something formal you could verify automatically. So let's talk a little bit about contracts, about design by contract. Let's start with the usual contracts as defined by or introduced by Bertrand Meyer. He designed the programming language Eiffel, which has contracts. So the contract allows the formal specification of an interface or interfaces for functions and classes, and enables the formal verification or the runtime verification. Formal verification during design time, or runtime verification during execution time, while the program is executed. The idea is to define pre and post conditions for every call, for example, invariants and side effects that then define the semantics of the functions and classes. I'll explain briefly what this means. And languages like ADA and Eiffel support the definition and validation of contracts for functions and objects. ADA is a programming language mainly used for avionics system, and Eiffel is not really used in practice in many projects. So, but Ada has already built in contracts. So let's have a look at an example in the language C. Most of you should be familiar with the language C. So there is no mechanism in C for contracts. So we can help ourselves by using asserts, for example. So it's just a very simple contract here now for square root function. The first assert makes sure that the incoming variables are correct. So in this case, they must be bigger or equal 0. If not, square root will fail. Then that's the precondition. So then we can call what the function is really supposed to do. So that's the netto content, that the actual work the function does. And in the end, we make another assert to check the post condition. The post condition is the result must be bigger or equal 0. If not, the function did not work. So that's the basic idea of pre and post conditions. You can also check invariance and side effects. Invariance would be, for example, if in a class or in a module, A always needs to be bigger than B. Whatever the class does or the module does, A must be bigger than B. That this would be an invariant. And the side effect would be, for example, if I do not allow side effect, I must not change variables in outside local function, for example. So this can, for example, be done by using the const keyword in C, but it's only a start of little elements you might do in C, but there's no real integration for formal description of contracts in C. Just to give an example. The problem with those contracts is it only works for synchronous functions and classes, so on unit level, basically. It does not help with asynchronous concurrent system. For example, if you want to integrate something on integration level or on system level, it's usually asynchronous and concurrent in an embedded system. So those kind of those kind of contracts do not help a lot on that level. And they are very fine-grained. So it's a lot of effort to bring all those functionalities, all those contracts into every function call. And in the end, it's a very low-level functionality. And also those contracts do not have states, they do not have history, they do not have execution orders, they do not have timing constraints. So, and those are all things you need to check in embedded systems. If not, it's not very valuable on that level for an embedded system. It has a big value, but it's a lot of effort. So let's have a look at contracts on a higher level. We use state machines as interface contracts. I'm going to give you a little example, again, in the language C, because that's most common in embedded systems. So imagine you have an API in the language C. So it's initialize, start, stop, function 1, 2, 3. If I ask you now, in which order am I allowed to execute things? For example, what do I have to do before I'm allowed to call function 1? Most people say, okay, you need to initialize, you need to start, then you can call function 1. Okay, but it's not, it's just, you get an idea because I named the functions semantically. But there's no clear specification what's allowed and what's not allowed. In the language C, you can call the functions in any order you want. So you can also make any number of errors there. And if I ask you, if I send stop, what do I have to do before I call function 2, for example? Do I need to initialize again? Do I need to start again? So what's the semantics there? That's unclear. So that's why we use a state machine to specify what's allowed, and everything else is not allowed. And that's the majority. The vast majority of cases are not allowed here. So in this case, now I can answer the question, What do I need to do before I call function 1? I need to initialize, and I need to start. And after I stop, I do not need to initialize again. I cannot initialize again, but I need to call start before I call function 2. So it's absolutely clear what has to be done. So you see already we have a benefit here for it's a very clear and a formal complete specification of the order of execution here that's allowed. Everything else is forbidden. So now let's have a look at the number of possible internal states, so execution paths in your software. So if you call any possible order for every function once, you already have 720 different orders just for those 6 functions, because it's the factor function here. And with the interface contracts, you only have 6 different paths to call. Everything else is forbidden. If you make a reset and call again, you already have a couple of 100 million possibilities, and in depth 3, it's a lot of numbers here. So, but if you only call the orders that are allowed here in the interface contract, you only have in depth 2 720 possibilities, and so on. So theoretically, you could still in depth 3 run a complete tests here for all the possibilities you have. So, but that's only the specification now. That's only the theory. How do I enforce this? So first of all, the benefit here is we have a massive reduction of execution paths or internal states by orders of magnitude. This enables much simpler systems and better testability, because we can cover all the paths that are allowed, but we have to prohibit the paths that are not allowed. And we have a very, very effective way to specify our interfaces. So now, what can I do now with the contract? I need to enforce this. First of all, I can specify my interfaces with contracts and generate the documentation in the requirements phase. That's already a very big benefit, because you always have a consistent specification for your interfaces that gives you more than just an API. No? It's much more than an API, because you have the complete semantics there. So then let's go on in the process. As you see, it's a V model. In the form, we can formally verify in the design phase in the models. So if I have a model that's capable of formal verification, that you cannot do this with code, or it's really hard to do it with code, and it's also, you also need the right modeling language to verify in design phase. But if you have that, you can verify while you're designing. So you do not even have to generate code or program or whatever. Already in the design phase, you can prove that the software is correct or that it's not correct. So then the next step is the test phase. So you can generate from the contract test cases for the dynamic test phase. And you can generate test cases to prove that your system works, or to prove that the system does not work according to the contract. And the last possibility here is to generate robust interfaces or monitoring interfaces between 2 components, for example, or between your system and the environment, to verify the correct behavior during runtime. And that's a low-hanging fruit, actually, because that's pretty simple to do, and it helps with basically any kind of system. So I'm going to show you 3 different tool sets for those 3 possibilities. Yeah, we also can generate the documentation, but I'll show this while I'm showing the tools. You can imagine how what the documentation looks like. So those are the 3 things I'm going to show. Let's start with the formal verification and implementation assistant in a modeling environment. So the idea is you model the structure of distributed embedded system, for example, or a concurrent embedded system. For every interface, you specify not only the syntax of the interface, so those are functions that can be called or messages that could be sent, but you also specify the interface contract. So that's the protocol semantics, the allowed order of execution, also the timing behavior of executions. So how long may it take, or what's the error condition for, what reply do I expect, and so on and so on. And then if you design a state machine attached to those interfaces, you get error messages and hints what you need to implement to make the state machine correct. So that's the first thing I'm going to show you. Model verification during the design phase. So next demonstration, I'm going to show you how we can specify use contracts to specify many test cases that try to break your system. That's a formal description, black box description of the black box behavior of your system, and a test case generator for path and data combinations to try to break your system, to prove in the sense that it works really robust. And the last, we use this, for example, for our Mini-Hill tool set for smallest possible hardware in the loop test system. That works completely automated, where we generate the complete test cases there. And the last demo I'm going to show you is the generation of robust interfaces during runtime that your system has no failures during runtime, because you might have communication partners that are not safe. External communication partners, components from another partner, for example, in a middleware for an avionics system. You design a middleware and you want to protect it with contracts, but you never know who is going to use this middleware. You have no access to those companies and to those partners or to those developers that actually develop software that uses your interfaces. Or in a machine control environment, who is going to send a job to my machine? So I want to keep complete control over what's going in and out of my system. That's just an idea to give you. Okay, so now I'm going to give you 3 live demos. The first is in our tool Trice. So that's the room method implementation. So it's we have Trice and we have eTrice, which is an open source implementation. I'm going to show you this now with the Trice tool. It's an implementation of the language real-time object-oriented modeling for concurrent real-time systems, and with a complete code generation. So whatever I show you is completely generated and in C or C++ and can run. So what's the idea? I have a component that implements or that controls a motor with a timeout. So we have a structure and we have a behavior. That's the behavior as a state machine. So this component has 2 timeouts and has a motor control interface. And here I have the state machine that controls the motor. So now here behind those interfaces, we have a protocol class. That's the formal interface description. So it's a motor control and it's a timeout specification, timer specification. So now let's have a look at the motor control specification. So we have start to position, done move to position, a stop and a stopped. Those are the incoming and outgoing messages into the system. So that's something, it's just an API, a bidirectional asynchronous API, but it's an API for a real-time system component, for a motor controller. So now let's add some semantics. If I start the motor, I expect either a done move to position, I expect an answer that it's been done, or if it's not done, I can, or if I want to stop it, I can stop it actively, but then I expect a stop message from the component I'm sending the message to. And here I could add more rules and so on. I also could add timeouts for certain movements and so on. So that's the basic idea. It's like an interface state machine. It's a little bit different format. It's a tree, not a state machine, but it could be expressed as a state machine as well. With newer tools, we've gone to state machines for that. Okay, so now I have specified the behavior for the motor control and the behavior for the timer. Same thing. If I start a timeout, I expect a timeout, or I can kill the timeout in and out. So that's the specification for the timeout. Now let's have a look at a component that wants to control a motor. So I'm going to start a motor now. So let's add some entry code to the state machine. I'm going to send start move to position 123. Okay. So now I'm going to send a message to the component that runs the motor. So now here you can see I started the motor. Now I could stop the motor, or I have to implement the done move to position transition. If not, my state machine is not complete. So I already, before I even generate code or run something or test something, I already know it's wrong. So now I can use this assistant to implement the correct behavior. Now I have a done move to position for the motor. And yeah, now the motor is done. Let's call this done. Still, I could, that's just a suggestion, I could also stop the motor, for example, if a timeout hits or so. Now I want to control the motor with a timeout. Let's say I add a timeout. I want to make sure that the motor is done after a certain time. Let's use the timeout 1, and let's add 1,000 milliseconds, for example. I start the timeout. Now, what happens? Now you can see at any time, any position here, at any state, the timeout might fire. So if it's not consumed, the timeout, I need to implement it here. So now I implemented the timeout tick. Let's call this timeout error. Now this motor is still running. So either I need to stop the motor, or I need to consume the done move to position. Both can happen. Now, in case of a timeout error, I'd rather stop the motor. So let's stop the motor. Okay, I stopped the motor, but I need to handle the stopped transition to make sure that it actually really stopped. So timeout error, and let's call this motor stopped. Okay, and here, if I'm done, I need to create a transition for the timeout tick, or I need to kill the timeout. But if the motor was positioned correctly, I'd rather kill the timeout, stop the timeout. We need this kill here. And now my semantic check here, my formal verification is satisfied. Now, what happens really, really often in embedded systems that you add another functionality at the wrong place. So, for example, new function. I add a new functionality here in another state, and I go there with another transition. Let's just take another transition, whatever it does. And suddenly I see, even if it has nothing to do with what I'm doing here, the motor is still running and the timeout is still running. So either I start the functionality at another place, or I must handle those functionalities here. Because if not, I will create race condition, and they will lead to potential bugs. And those are bugs that are really, really hard to detect. So formal verification is really a very nice thing to have, but you need the right tools for that. That's a lot of effort, of course, to change to a new method if you don't have the right tools already in place. But it's for highly critical systems, it's really worth the effort. Okay, so that's the first demonstration during the design phase. So let's move on to the test phase. Let's have a look at our mini hill. That's this hardware I've shown, hardware in the loop system. I just want to show you the definition of a contract for test cases. So we create a state machine that defines all the states as a black box behavior your system might be in. And between all those states, we have transitions to define what can happen here, what can happen or what must not happen. That's the more interesting part. Huh? So in this case, I set the speed, for example, to 10%, 50%, or 90%. By that, doing the equivalency classes in my test cases. Then the motor is running. Then I could change the direction. I could brake the system. Then the motor is stopped. I could go back, do the same again. So it's just a very simple example. So, and now what our system does, it generates a test case for every pass between initial and end. So every pass gets his own test case. Also, the loops, in case of a loop, it needs to generate all the paths again. And of course, it needs to stop at a certain point. And that's what we have those metrics here for. So we have a specified metric, it's called end switch, that knows how to stop the generation process. So now let's have a look at what test cases we generate from that. So those are all the test cases we generate for this for the state machine. So that's what we design and that's what we get. And it's also test cases also generated in C code, and they can be executed automatically as hardware in the loop or software in the loop test. So, and by doing that, you find a lot of race conditions in your software, and especially things that are really, really hard to detect, because it's really hard to write those test cases manually. And the contract gives you a really deep insight into what needs to be generated here. Okay, so now let's modify this specification a little bit. Let's say, okay, I want to add two more equivalency classes. So I want to add an equivalency class for 1% of the motor speed and 99%. This would be a typical approach with boundary analysis. For example, you would have some more values here. Here you see you have 5 more transitions. As I said before, that's a black box behavior. It's not your state machine you try to test. It's the state machine that describes what you expect your system to do. And you can do this on any level, on component level, on integration level, on system level, because it's asynchronous. So now let's do something else. Let's assume we go back from, while we are braking, we want to go back to you are active, for example. So we are in the state brake, and now we want to go back to you are active because we want to restart the process. And while we're doing this, we want to check whether, let's say, we have activated the motor control, whatever it is. So on every transition, of course, we run a little test case that checks that this path is correct or not correct. It's also attached to an action and a reaction here. So now I created a couple of more transitions. Let's generate the test cases again. So I'm generating documentation and the test cases. But of course, we have a look at not at the C code, but at the generated documentation. So now let's have a look at this. And here you see we do not have 15 test cases, but 25 test cases, because we have all those paths more. So for example, we have this new transition. Yeah, here, for example, the 99 at the 1, and it tests all the combinations necessary according to the metric here. So let's up the metric a little bit. Let's make it a little bit higher. That makes it really interesting now. So I'm going to set the end switch metric to 3. So it's a combinatorial approach. It tests all the combinations of all the transitions of locally 3 states, all the combinations of data and transitions. I don't go into detail now, but I'm going to show you what happens. So it takes a lot more paths now. It generates a lot more paths now. And let's have a look at the generated documentation. And here you see all the test cases that are generated. So we are talking now about something like a couple of hundred test cases, maybe 233 test cases. And you can imagine if you test all those data combinations and path combinations, you get a really, really deep, exhausting test for your system. Helps a lot to find sporadic errors, robustness tests, and so on. So it's a really nice method here. So that's the second step. So that's what you can do during test time. So you create a model. So you don't need a formal model for your application. It can be C code, it can be assembler if you want, because it's a black box test. So we call the functionalities on the outside, for example, with signals as a hardware in the loop test, or as a software in the loop test is also possible. So that's something that's non-invasive. So then the third step, or the third possibility I'm going to show you again with a contract, it's for C code. So imagine you have a programming in C, and you want to make the program more robust. So what you can do usually at strategic interfaces, for example, at interfaces to the outside world or to other strategic components, you create a contract. So let's have a look at such a contract in C. So we have an interface definition language where we can define C interfaces. So from this C interface, we generate the code for the implementation. So for example, we have an initialize function, we have a check UI, handle, go standby function, and so on. And we just generate a C interface for those functions. So that's the generated code for the C interface. Then we have a service one implementation. That's a state machine that implements the interface check as a filter, if you want. And then we have an implementation interface, again, the same interface, but we hide the real implementation behind this interface. And of course, that's what you need to implement. Everything else is generated. So now let's have a look at the interface contract again. That's the interface specification, but we add to the interface specification, we add checks. For example, checks for ranges, checks for invariants, checks for side effects, and so on. So for example, in the interface here, the value I must be in a range of between -3 and +3. That would be the regular low-level contract. But additionally, we can create an interface state machine. So that's an interface state machine where I describe exactly what's allowed. Everything else is not allowed. So for example, I add a new state blah. Now I have a new state, and I can say, okay, make another transition from init. From init, I can go to the state blah by calling function, or let's say handle function, for example. Yeah. So now I created a different semantic here. I'm going to delete this again because it doesn't make sense here. Also the blah state. So, and now I'm generating the code for this service, for the implementation of the contract. And for all the interfaces, the only thing I did, I implemented the implementation for the service here manually. So that's what I really did. Doesn't matter what it does, because I want to check the contract. And I'm going to call the functionality, in this case, from my main function here. Yeah, from a main function, I call this functionality. Now I'm going to run my system. So it's generated, compiled, and everything is okay. I only have valid sequences. I can check what I actually did. So that's what my program did. As a sequence diagram, it called those functionalities, and everything is okay. So no red functionality. So during runtime, my program behaved correctly. Now let's be ugly here. So I'm going to add, as a programmer, I'm adding some more functionalities. I'm going to, for example, to start processing, or let's call handle, or let's call initialize after I go to standby. So let's do that. And I just modified my program. I'm going to generate everything again, and I see immediately, while the program has been running, I detected a problem here. Now I could evaluate this message, or I could jump to the sequence diagram and see exactly what happens. I've been in standby after the go standby functionality or function call, and I called initialize. That's exactly what I did. Remember, I entered the initialize function after go standby. So you see exactly what happened, exactly at the right point in time. If you have activated the time logging, for example, the timestamp, exactly the order. So you could even give the other, the guy who programmed the other side, and this sequence diagram to find out what he actually did. This helps a lot in identifying the problem in the program code. So now let's fix this again. Let's restart the contract here and the test. So that's the test during runtime. You see, it's clean everything again. Okay, so those have been the little demos I wanted to show you. What are the typical use cases for those contracts now? You can protect your system at the external interfaces. So, for example, incorrect behavior of other systems, like user behavior at a graphical user interface. It could also be an attack, or just a wrong behavior of another system. So, for example, in a crane that uses a lubrication pump with a safety critical, if the crane does not behave correctly against the lubrication pump cannot work correctly. But the lubrication pump, in this case, or one of our customers, sends the answer to the crane system and tells exactly what's the problem. Either the lubrication pump didn't work correctly, or the crane did not behave correctly. But in any case, it's better to detect the problem and shut down the system or throw any kind of error. So that's very important. And we can do this by generating an interface monitor that monitors everything during runtime. Then we can implement complex behavior fast and correctly. For example, with the model verification and the implementation assistant. So while you're modeling, every little bit you do is checked if you have a contract for that. You cannot get around this contract, even while you're developing. So your system, by the way, also gets much simpler because you do not need to check every little detail every little time when you call something, because you know the contract is much more reliable than what you as a programmer usually do. So all the redundant error checks for null pointers and so on. Then you can have a redundant and diverse implementation of safety monitors. So if you have your functionality, which is usually very complex, you can be able to create with those contracts a redundant and diverse implementation for those safety monitors that run on a separate processor, for example, and implement specify and implement the safety rules And then you can generate the runtime monitors to check all those safety rules during runtime. A very nice formal approach that helps you really to implement high-level safety monitors or security monitors as well. And it's also easy to find bugs, or it's easier to find bugs that are usually hard to find. For example, sporadic race conditions. You have a problem with one customer application of thousands once a year. It's almost impossible to find this kind of error. Yeah? So how would you try to debug that? And by specifying expected behavior and generate lots and lots of combinatorial test cases that try to break your system, you find not all the race conditions, but quite some race conditions and sporadic errors in your application. And there are many, many other use cases. So just to give an idea what you can do with those kind of approaches. By the way, all the tools I've shown you are in projects, in many, many projects for at least between 5 and 20 years. So it's proven in use. Yeah, just to mention that. So if you have any questions, please don't hesitate to contact us, Annette at Eclipsina or me at Protos. And yeah, I've been glad to be here. I hope you enjoyed this little presentations, and thanks to Annette again for the possibility to be here. Yeah, back to Annette. Thank you.
Sorry, I was muted. Thank you, Thomas, for this great technical talk today. And I'm looking forward to additional topics which we still have in the pipeline. But it's always a pleasure to see how the things are working together and how much you can do if you are working on an architecture level to an early stage of a development. Thanks again, and also to the audience, thank you for joining, and I hope you will come back for the next talk. Thank you, and bye-bye.
Bye-bye.